Hello. Today I plan to do one more problem involving dimensional vector spaces, and then we move on to diagonalization and applications. Example 1, dimensional vector spaces. So let A be the matrix 1, 2, 0, 1. Define the following vector space. P is a set of all matrices X, capital X, which is A, B, C, D. So the vector space V consists of all matrices X, 2 by 2 matrices, A, B, C, D. Vertical bar with the property that AX equals to XA. So the problem is find the dimension of V and a Bayesian V. Bayesian V, so in this case, the quote-unquote vectors are matrices. So the realization of vectors are matrices. A basis means a basic set of matrices, as every matrix in V can be written uniquely as a linear combination of those basis matrices with real coefficients. Solution. Let's take a closer look at AX equals to XA. Means A is 1, 2, 0, 1 multiplied by A, B, C, D equals to A, B, C, D multiplied by 1, 2, 0, 1. Let's try to write this equality more component-wise, in other words, in detail. So what we have on the entry 1, 1? Right. Let's mark the equations according to the entry. On entry 1, 1, first row, first column. So first row, first column is first row, first column. So what does it mean? A plus 2C equals to first row, first column is A. It's easy. So that means essentially that means C equals to 0. But let's try to wait a little bit. So A plus 2C equals to A. Entry 1, 2, first row, second column. First row, second column. B plus 2D equals to first row, second column. 2A plus B. 2, 1, second row, first column. Second, first. So C equals to second, first. C equals to C. So non-information. So we can discard it anyway. So 2, 2. Second, second. Second row, second column. So that will be a D equals to second, second. 2C plus D. So what can we infer from this? So because A plus 2C equals to A, like I said, C equals to 0 will do the job. So from this one, we know for sure that C equals to 0. Circle it, keep it in mind, very important. If C equals to 0, the last one completely irrelevant because D equals to 2 times 0 plus D. So we don't really care about it. So it's automatically true. Again, this one is automatically true because C equals to C. Okay, so far we know that C equals to 0 and the second one. So what can we make of the second one? B, we can cancel a B with a B, and 2D equals to 2A. So what would be another important relation? A equals to D. So essentially we got two, so to say that AX equals to XA as a commutation relation means the same as to say C equals to 0 and A equals to D. So In other words, the matrices in the vector space V are the matrices A, B, C, D with the property C equals to 0 and A equals to Z. So matrices of V, matrices as in quote unquote vectors of V are vectors of the form. Okay, so C equals to 0. So remember A, B, C, D. C equals to 0, 0 here. A equals to D, so put A here. And instead of D, still put A because D is the same with A. And B could be anything, so put D here. So for every vector, which is a matrix in V, this vector is of the form A, B, 0, A. So in other words, the vector space V consists of entities of this type, A, B, 0, A. So what is the number of independent parameters needed to completely describe an item in the vector space V? There are two of them. So clearly the dimension of V is 2, because we have two independent parameters A and B needed to completely describe any vector in the vector space V. And what is a base in V? So okay, so just to see better here. Base in V. So that's a very useful routine. If we have, here we got the parameters A and B, set one parameter 1 and the other 0. So if we set A equals to 1 and B equals to 0, we'll get the matrix 1, 1, 0, 0. There's one element of the basis. And then if we set A equals to 0, B equals to 1, we get 0, 0, 0, 1. So here we set A equals to 1 and B equals to 0, we got this vector. Set A equals to 0, B equals to 1, we got this vector. So we got dimension of V is 2 because we need exactly 2 independent parameters to completely describe a quote unquote vectors in matrix in the vector space V. And then the basis in V consists of two matrices, identity matrix and the matrix of one upper right order only. Okay, then, so let's move on. Now let's move on to so this requires a bit of reading, because I suppose that you read something about diagonalization, and then we'll do an application to diagonalization to a concrete problem. Yeah. Okay, so exercise 2 for me. Let A be the matrix this here. 2, 1 equals row minus 2 and 5. So that A is diagonalizable. Find the diagonal for B. And the diagonalizing matrix T, I put again like a different requirement, find diagonalizing matrix T. Then apply this information to find A to the power n. To find an explicit formula for A to the power n. So let me put, I want more questions and find explicit formulas for, first of all, A to the power n and the exponential of AT. T being a scalar. This covers a lot from the diagonalization chapter. Okay. So given the matrix A, 2, 1, minus 2, 5, show that A is diagonalizable, find the diagonal for D, find the diagonalizing matrix T, and apply this information to find explicit formulas for the nth power of the matrix, A to the power n, and the matrix exponential E to the power AT, exponential of AT. Okay. Okay, I need to erase a little bit this so that I need more space. Okay, so let's do the first one, first solution. First of all, let's do to find eigenvalues of A. Okay, so let's do the work here. The eigenvalues are obtained by solving the equation determinant of A minus lambda identity equals to 0. So solve the determinant of 2 minus lambda. So subtract lambda from the diagonal. 1, so we don't subtract anything here. Minus 2 and 5 minus lambda. The determinant equals to 0. So 0 equals to the determinant of 2 minus lambda, 1 minus 2, 5 minus lambda. So let's try to do this determinant. The determinant of a 2 by 2 matrix is the product of the main diagonal with plus, minus the product of the secondary diagonal with minus. So this will be 2 minus lambda times 5 minus lambda minus 1 times minus 2, so plus 2, which will be lambda squared minus 5 lambda minus 2 lambda minus 7 lambda here plus 10 plus another 2 plus 12. So 0 equals to all the way to lambda squared minus 7 lambda plus 12 equals to, how to figure this one, lambda minus 3 times lambda minus 2, right? Lambda minus 4. Lambda minus 3 times lambda minus 4. Okay, so we need to find lambda 0 equals to lambda minus 3 times lambda minus 4. So lambda 1 equals to 3, lambda 2 equals to 4. I'll write the result here and then I erase the work. So keep the fruit of the work. Lambda 1 equals to 3, lambda 2 equals to 4. Therefore, since the matrix has distinct eigenvalues, offhand we know that it's diagonalizable. But now we have to fill in the details. So we just found eigenvalues 3 and 4 so far. By solving the characteristic equation of the matrix, the determinant of A minus lambda identity equals to 0. In this case, a quadratic equation. We did it, and then let's keep the result in mind. So far, we got eigenvalues. Okay, so step number 2. Find the eigenvectors for every eigenvalue for 5 corresponding eigenvectors. So let's do eigenvectors. So we have to find an eigenvector for lambda 1 and an eigenvector for lambda 2. For lambda 1, so for lambda 1 equals to 3. Solve the following system. The matrix obtained by subtracting 3, because remember, A minus lambda I is the characteristic equation. Subtract 3 from the main diagonal. So 2 minus 3 here is minus 1. From this upper right one, nothing. Don't subtract anything. Leave this one alone again, minus 2, and subtract 2. So subtract 3 from the diagonal entries. So 2 minus 3 is minus 1. 5 minus 3 equals to 2. So this is the matrix A minus 3 identity. So this is A minus 3I. So which is minus 1, 1, minus 2, 2. I want to find the eigenvector. Let's call this eigenvector PQ. This eigenvector equals to 0, 0. Now, we have to solve this system and find a non-zero eigenvector. So this means what? First, minus P plus Q equals to 0. And then the second one, because we should get a non-zero vector, it should be not proportional, it should be proportional with this one, be the same. So minus 2P plus 2Q equals to 0. So essentially, everything boils down to P equals to Q. So if P equals to Q, the eigenvector should be any vector which is non-zero, vector of the for PQ with P equals to Q. So we can take V1, the first eigenvector equals to 1, 1. Very important. So we get a big success here. We got an eigenvector corresponding to the eigenvalue lambda 1 equals to 3. For lambda 1 equals to 3, we got the eigenvector v1 equals to 1, 1. For lambda 2 equals to 4, what do we get? Again, exactly like in the first derivation of the eigenvector for lambda 1 equals to 3. Now we find the eigenvector for lambda 2 equals to 4. Subtract 4 from the diagonal entries of A. So we'll get 2 minus 4 upper left is minus 2, 1. Minus 2, leave it alone. And 5 minus 4 equals to 1. So minus 2, 1, minus 2, 1, multiplied by the vector PQ equals to 0, 0. So here on the left, we get A minus 4i, 4 times identity matrix times the vector V, eigenvector equals to null vector. A minus 4i times V equals to null vector means A, V equals to 4V. Right? Okay, so let's try to elaborate. What does it mean? Row dot column. Minus 2p plus q equals to 0, and then the other one is the same, right? So what will be v2? V2 will be 1, 2. Because we get minus 2 times 1 plus 1 times 2 equals to 0. So that's v2. Okay. So we just for every eigenvalue, so that's an easy case. So if the eigenvalues of the matrix are distinct, for every eigenvalue, find an eigenvector. The eigenvectors will be linearly independent, and they will constitute the base of the Rn, in this case of R squared. Right? Okay, so let's keep the fruit of the work and erase the work. Okay, so eigenvectors. We'll put v1 equals to 1, 1 for lambda 1 equals to 3. Okay, we got this. And for v1 equals to 1, 1 for lambda 1 equals to 3. And the eigenvector v2 equals to 1, 2. Eigenvector for lambda 2 equals to 4. Okay. That's very important. So that's the first important 2 steps you have to do. Find the eigenvalues. For every eigenvalue, find an eigenvector. Okay, now, at this moment, what will be a diagonal form? The matrix is diagonalizable because it has distinct eigenvalues. Diagonal form of the matrix A, diagonal form will be D equals to 2, 1 minus 2, 5. This matrix A. So diagonal form, we have to put eigenvalues on the diagonal. So 3 was the first eigenvalue, 4 is the second eigenvalue, and 0 and 0. 3, 0, 0, 4. This is a diagonal form of A. A diagonalizing matrix. Diagonalizing matrix. To be T. Diagonalizing matrix is the matrix contained by stacking the eigenvectors as columns. For the first eigenvalue 3, stack the eigenvector 1, 1. That's the first column. For the second eigenvector 4, stack the eigenvector 1, 2. So that's the diagonalizing matrix. So diagonal forms answer 2 important questions. Diagonal form is this one. And diagonalizing matrix T is this one. So what does it mean? It means that A equals to T, D, T inverse. Since we got here, let's write down on the spot because we need it later. T inverse is 1 over determinant of T. Determinant of T is 1 times 2 minus 1 times 1 is 1. So determinant is 1. So how to find the inverse? Flip the main diagonal elements. So 2, 1 here. Then minus 1, and switch the sign of the secondary diagonal. So the diagonalizing matrix. That's the inverse of the diagonalizing matrix. So what's important? A equals to T dt inverse. So this is important because we can find any function in principle, any analytic function of A by using this formula. So anyway, so instead of A, we can put any function of A. This implies any f of A will be T times, or D will be f of 3, 0, 0, f of 4, the inverse. Right. That's be prepared to use any reasonable analytic function, exponentials, strict functions, you name it. You can find any function of a matrix by using this formula. Okay, so now we need a to the power n. In particular, a to the power n will be t times d to the power n. The nth power of d is easy to calculate. So t times 3 to the power n, 0, 0 for the power n times t inverse. That's a to the power n. Okay, so let's try to, so this which will be what? T, we've seen that T is 1, 1, 1, 2. 3 to the power n, 0, 0, 4 to the power n is just the matrix A to the power, D to the power n. So 3 to the power n, 0, 0, 4 to the power n. So T, D to the power n, T inverse will be from there 2 minus 1, 2 minus 1, minus 1, 1. So that's the explicit formula for a to the power n. Okay, so now I need to free some space here. So one more time. So a to the power n equals to t, which will be again 1, 1, 1, 2 times, again, let me put it again here. Okay, let's multiply these two. Beware not to switch. So I mean, we don't want to switch the first and the second. So we can multiply the second and the third, but by keeping them in the same order. So what will be this one? Second and third. 2 times 3 to the power n. So first one. 2 times 3 to the power n, then minus 3 to the power n, then minus 4 to the power n, and 4 to the power n. Which is first. 2 times 3 to the power n minus 4 to the power n. 2 times 3 to the power n minus 4 to the power n. First second. 4 to the power n minus 3 to the power n. Second first. 2 times 3 to the power n minus 2 times 4 to the power n. Two times 3 to the power n minus 2 times 4 to the power n. Second. 2 times 4 to the power n minus 3 to the power n. 2 times 4 to the power n minus 3 to the power n. And that's the answer. That's the explicit formula for this for a to the power n. That's the formula for a to the power n. So if we raise the matrix A to the nth power, we get a very nice explicit formula like this. We don't have to separate this, but I just want for a better view, right? So how to do this, how to test this one? So check. If we set n equals to 0, what should we get? A to the power 0, we should get identity matrix. Identity matrix is 1, 0, 0, 1. Do we get 1, 0, 0, 1? If n equals to 0, all the exponentials are 1. So 2 minus 1 is 1. 1 minus 1 is 0. All the exponentials are 1. 2 minus 2 is 0. 2 minus 1 is 1. So we get 1, 0, 0, 1 identity matrix as expected. Let's check n equals to 1. For n equals to 1, a to the power 1 should be the same in this matrix. We should get 2, 1 minus 2, 5. If n equals to 1, it would be 6 minus 4 is 2. Right? 4 minus 3 is 1. Right? Then we get 2 times 3 is 6 minus 8 is minus 2. Everything was nice. And finally, if n equals to 1, we get 8 minus 3 is 5. So this works, right? Okay, so next, the other question was to use this information of diagonalization to find the exponential of AT. Okay. It's very similar, so the same type of method. Exponential of AT. Everything transfers to the diagonal form. So like we got here, a to the power n is t times d to the power n, t inverse. Exactly in the same way, exponential of AT is t, capital T, times exponential of dt. So e to the power 3t. So apply the exponential, the function e to the power at to each eigenvalue. E to the power 3t, 0, 0, e to the power 4t. Times t inverse. I put t inverse here. There's the formula for exponential of AT. So in other words, the exponential function, exponential of AT, applies to the diagonal entries 3 and 4. Exponential of 3t, exponential of 4t, e to the power 3t, e to the power 4t. And then, of course, with capital T on the left, capital T inverse on the right, like we did here. Okay, so let's erase the unnecessary things now. So what will be this? It will be E will be 1, 1, 1, 2. Then e to the power 3t, 0, 0, e to the power 4t. And t inverse will be, well, 2, 1 on the main diagonal like we did before, and then minus 1, minus 1. Okay, so as before, we have to multiply these two together and then keep this here. So this will be 1, 1, 1, 2 multiplied by. Now let's multiply the second and third. First. 2 e to the power 3t. 2 times e to the power 3t. First, second. Minus e to the power 3t. Second first. Minus e to the power 4t. Second here. E to the power 4t. Equals. Now, first. We get 2 times e to the power 4, 2 times e to the power 3t minus e to the power 4t. So 2 times e to the power 3t minus e to the power 4t. First, second. E to the power 4t minus e to the power 3t. Second first. 2 e to the power 3t minus 2 e to the power 4t. And second, 2 e to the power 4t minus e to the power 3t. So this will be the matrix exponential of AT, t being a parameter. And these are the four elements of exponential of AT. So another way is one more time. So another way to quickly check if we set t equals to 0, what we should get? If the parameter t is 0, it's exponential of a times 0. A times 0 is the null matrix. Exponential of the null matrix is the identity matrix, right? So if we set t equals to 0, we should get identity matrix. So check. If we set t equals to 0, we get identity matrix 2 by 2, I sub 2. Do we get identity matrix or not? So if t equals to 0, all the exponentials become 1. So 2 minus 1 is 1. So 1 here. 1 minus 1, 0. So 1, 0. 2 minus 2 is 0. So 1, 0, 0. And then there is 1 on the right, on the lower right. So 2 times 1 is the exponential of 0 is 1. 2 times 1 minus 1 is 1. So if t equals to 0, we recover the identity matrix 2 by 2. Okay, so pretty much the basically more complicated area. So we have to do more work on this diagonalization, but this is the first starting point, and then we'll continue tomorrow with other problems of diagonalization. This is the last topic of the linear algebra part. After this linear algebra part, we'll move to Laplace transforms. So I'll see you tomorrow then.